Each component in a power system has impedance, whether it is a source, a transmission line, or a load. This total system impedance limits the magnitude of current that will flow through the power system. In the power system seen here, we have a total system impedance of 230 ohms. If the source were generating power at 230 kilovolts phase to neutral, 1,000 amps of current would be supplied to our load. If a fault occurs on the power system in a location that cuts off the path of current flow to the load, the total impedance of our power system changes to only 23 ohms. Due to the drop in impedance, our current level now increases substantially. The operating principle of distance protection for transmission lines works in the following way. The magnitude of current and voltage is measured at the beginning of the transmission line, and using these measurements, a ratio of the voltage over the current is calculated. This ratio gives a value that is equal to the impedance of the total power system. When a fault occurs on the power system, cutting off the path of current to some of the load, the impedance of the power system will decrease. This decrease in impedance will cause the current to increase and the voltage to decrease slightly, thus changing the ratio of the voltage over the current to match the new impedance of the line. The reason that the voltage will decrease is because the only voltage drops that now occur are across the transmission line and the source impedance. In the example shown here, the fault is located after the transmission line but occurred before the majority of the power system load. Now the only impedance on this power system is the impedance of the source and the transmission lines before the fault. When this fault occurs on the transmission line, thus cutting off the path of current to some of the load, the system impedance will decrease. This decrease in impedance will cause the current to increase and the voltage to decrease. This changes the ratio of current over voltage to match the new impedance of the line. Distance relays are programmed to know the impedance to the end of the transmission line. If the impedance the relay calculates is less than the impedance of the transmission line, it will know that the fault is on the transmission line and trip the circuit. The term distance is used because by comparing the calculated impedance of the transmission line with the known impedance of the transmission line, it can be determined how far along the transmission line the fault has occurred. In our example, the fault occurred at a distance of 50% of the entire transmission line. The impedance of the transmission line is often drawn on an RX diagram. The x-axis represents the resistive component of the impedance of the line. The y-axis in the positive direction represents the inductive component of line impedance, and in the negative direction, the capacitive component of line impedance. The impedance of a transmission line is inherently mostly inductive. If the impedance of the line were plotted on this graph, it would be shown very close to the y-axis. If a line is drawn from this point to the origin of the graph, we now have a representation of the entire transmission line. For example, plotting a point on the line midway between the origin and the end of the line would give an impedance of 10 ohms. This would also be the impedance of the midpoint of the transmission line. In a normal power system transmission system, there is a load at the end of the transmission line. Typically, this load is mostly resistive and has a larger impedance than the rest of the power system. Therefore, if you were to plot the impedance of a power system under normal condition on an RX diagram, the point would be shown very close to the x-axis. The distance from the origin would be the magnitude of impedance of the transmission line and the load. If a fault to the ground were to now occur at the midpoint on the transmission line, all of the impedances after the point of fault would no longer be part of the power system. The impedance of the system would now only be the impedance of the source plus the impedance of the transmission line before the fault. The power system impedance is now no longer mostly resistive because the only impedance is now the mostly inductive transmission line. Therefore, the plotting of the measured impedance on the RX diagram will be very close to the y-axis. Now the impedance point will fall along the line drawn from the origin to the impedance of the entire transmission line. Since we know that the distance to the fault is actually closer than the length of the entire transmission line, it is in the zone that we are protecting. Therefore, we can send the signal to trip the breaker and clear the fault. To program distance relays, you need to configure the impedance of the line, where any impedance less than this value will indicate a faulted line. This is done in modern distance relays by creating zones of operation on the RX diagram. If the impedance calculated at the point of measurement of the power system ever falls within this zone, the relay will trip. These zones fit into one of the following categories: an impedance zone, an admittance or Moe circle zone, a reactance zone, a resistance zone, and a quadrilateral zone. The zone of protection shown here is known as an impedance zone. Any impedance that falls within the radius of the circle indicates a fault that needs to be cleared. The reach indicates in ohms how far on down the power system the zone of protection extends. This type of zone is inherently non-directional and will detect faults that occur in the reverse direction away from the point of measurement. This type of impedance zone is normally used for generation backup protection. The next zone of protection is known as a reactance zone. This type of zone is used to detect when the impedance of the fault has a very high resistive component to it. A fault with high resistive impedance indicates there is a load on the transmission line, and the fault is most likely not on the transmission line. This type of zone is usually never used to trip a transmission line on its own, but is normally used to supervise another distance zone of protection. For example, if an impedance zone detected the impedance of the line enter its zone of protection due to an external fault, the reactance zone can be used to block the impedance zone from tripping because it can determine that the impedance is mostly resistive, and therefore the fault is not on the transmission line. The zone of protection shown here is known as a resistance zone. This type of zone is used to detect when the impedance of the fault has a very high inductive component to it. A fault with high inductive impedance indicates that there is very little or no resistive load at the end of the transmission line, and it is likely that the fault is located on the transmission line itself. There are two boundary lines that can be set for this type of protective zone. These boundaries do not need to have the same setting on the x-axis. This type of zone is usually never used to trip a transmission line on its own, but is normally used to supervise another distance zone of protection. For example, our impedance zone detects the impedance of the line just slightly enter its zone of protection due to a fault occurring towards the end of its zone of protection. Now the resistive zone can be used to verify that the fault is actually on the transmission line, because the impedance of the fault is mostly inductive. In this configuration, the resistance zone would be giving the impedance zone permission to trip. The next zone of protection is the admittance or Moe circle zone. A Moe circle zone is the most common type of protection zone that is used in transmission line distance relays. A Moe circle zone detects whenever the impedance of the transmission line falls within the area defined by the Moe circle. This type of zone is inherently directional and will not detect faults that fall in the reverse direction of the transmission line, since that point will fall outside of the circle. The reach of the zone of protection shows in impedance how far down the transmission line this zone will protect. The reach always lies along the line of the impedance of the transmission line, which is usually around 75 to 80 degrees away from the x-axis. The reach is also the point in the circle that is the farthest away from the origin of the graph. One of the reasons that the Moe circle is positioned where it is along the graph is so the zone of protection will not trip on a power system that is highly loaded. For example, on the power system seen here, the reach of our Moe circle was programmed to be 18 ohms. Under normal circumstances, where there are no faults on the power system, the impedance of the power system will be very large, and the plotted measured impedance on the Rx will be located close to the x-axis. If a substantial amount of load is added to the power system, the current needed to feed the load increases substantially. Even though there is no fault on the transmission line, the newly calculated impedance of the line would be less than the reach of the Moe circle zone. However, since the load that was added is mostly resistive, the plotted impedance point would be much closer to the origin of the graph, but still very close to the x-axis, as seen here. Since the Moe circle is positioned where it is on the graph, there is very little area included in the zone of protection in the resistance direction. Therefore, the new impedance will not fall into the zone of protection, and the relay will not trip. Many advanced microprocessor-based relays, such as the D60, give the user the ability to further customize the shape of the Moe circle to meet their protection needs. For example, if this power system has instances where it can be heavily loaded, which may cause the impedance of the line to encroach into the Moe circle, the shape of the circle may need to be changed to not include this area in the zone of protection. The Moe zone can be altered to form a lenticular shape, which only allows tripping when the impedance falls very close to the angle of the transmission line impedance. Therefore, highly loaded systems, which cause the impedance point to approach very near the origin, will not result in tripping the transmission line. As a side note, the D60 relay also gives the protection engineer the ability to configure the mho characteristic into what is known as a tomato-shaped zone. A tomato-shaped mho characteristic allows for faults that have more of a resistive element to fall into its zone of protection. The D60 relay also allows you to create what is known as a quadrilateral zone of protection. This type of zone allows you to set the reactance and resistive upper and lower boundaries to create your own custom shape to match the needs of your power system. In this type of zone, there are essentially three reaches, one in the inductive direction, one in the positive resistive direction, and one in the negative resistive direction. The D60 relay has added some additional features to the mho circle characteristic to increase security and reliability for faults that occur very close to the point of measurement. On faults that occur very close to the point where the currents and voltages are being measured, relays may have difficulty distinguishing whether the fault is inside their zone of protection or outside of it. To overcome this difficulty, the D60 changes the size of the mho circle when the calculated impedance is very near the origin. This is known as the expansion mho element. If a fault occurs just before the beginning of the transmission line, and the transmission line is double-ended or multi-ended, current will flow into the CT from the opposite direction. If the D60 now calculates the impedance of the line, the value will be negative, and plotting that impedance point will put it very near the origin, but in the reverse direction to the transmission line. To make sure that the mho characteristic does not mistake this as being an internal fault, the relay recognizes the low impedance of the line, sees that the value is negative, and shrinks the radius of the circle. Since the mho circle is no longer near the origin and the location of the fault, there is no chance in the relay false tripping. Notice, however, that the reach of the mho circle did not change and still extends out to the end of the original zone of protection. If a fault occurs just after the beginning of the transmission line, current will flow into the CT from the positive direction. If the D60 now calculates the impedance of the line, the value will be positive. Plotting that impedance point will put it very near the origin in the positive direction of the transmission line. To make sure that the mho characteristic does realize this as being an internal fault that needs to be cleared, the relay recognizes the low impedance of the line, sees that the value is positive, and enlarges the radius of the circle. Since the mho circle now extends past the origin to include a larger area, the location of the fault is sure to fit in the zone of protection, and the fault can be cleared properly. Notice that the reach of the mho circle does not change and still extends out to the end of the original zone of protection. The D60 implements the expansion mho element by using a feature that is known as voltage memory polarization. We will use the following example to demonstrate what voltage memory polarization is and the effect it has on the shape of the mho circle characteristic. The power system shown here has a source that is generating power at 230 kilovolts. If a fault to ground now occurs right around the point of measurement, but before the beginning of the transmission line, the impedance of the power system will now be equal to just the impedance of the source. This means that the 230 kilovolts will drop to zero over the distance of that source impedance. This will result in the magnitude of voltage being read at the point of measurement being 0 volts. The current will be read as coming from the direction opposite to the source if this is a double-ended or multi-ended transmission line. If the D60 calculates the voltage over current impedance ratio, the measured voltage would be 0 and the current would have a negative value. This would result in an impedance of close to -0 ohms. For an impedance value such as this, it would be difficult for the D60 to determine whether to expand the size of the mho circle or shrink the size of the mho circle. Essentially, the voltage memorization feature detects that the voltage has gone to 0 and uses the magnitude of the voltage before the fault occurred to detect whether the fault is inside the transmission line zone of protection or outside the transmission line zone of protection. In other words, it is checking the direction the fault is located with respect to the measurement point. When the D60 uses the memorized voltage, symbolized as Vm, which is equal to the value of the source voltage of 230 kilovolts, the calculated impedance is a negative number. This is a sure indication that the fault is located outside of the transmission line zone of protection, and the D60 would shrink the size of the mho circle characteristic. Now the impedance calculated by the D60 is well outside the zone of protection. If the fault occurs on the transmission line just past the point of measurement, the impedance of the power system is the value of the source impedance plus the very small impedance of the unfaulted part of the transmission line. For most purposes, we can assume this to be 0, so the impedance of our power system would be the impedance of only the source. As in the previous example, the 230 kilovolts will drop to 0 over the distance of the source impedance. This will result in the magnitude of voltage being read at the point of measurement to be 0 volts. This time, the fault will be fed from our source and the current will be measured as flowing in the positive direction. As in the previous example, the D60 will calculate the impedance to be close to positive 0 ohms. For an impedance value such as this, it is difficult for the D60 to determine whether to expand the size of the Mohs circle or shrink the size of the Mohs circle. If the D60 used the memorized voltage from the period before the fault occurred, which is 230 kilovolts, the calculated impedance will now be a positive number. This is a sure indication that the fault is located in its zone of protection, and the D60 will expand the size of the Mohs circle. Now the impedance of the line that is calculated by the D60 is well inside the zone of protection. You may now be wondering by how much the expansion Mohs characteristic will shrink or stretch the size of the Mohs circle. The D60 will always modify the size of the Mohs circle by a value that is equal to the source impedance of the power system. For example, the normal reach of our Mohs characteristic is programmed to 18 ohms, and the D60 detects that a fault occurs on the source side of the transmission line, but very close to the measurement point. The D60 will shrink the size of the circle by an amount equal to the source impedance. In our case, our source impedance is 3 ohms. Therefore, the expansion Mohs element will shrink the size of the Mohs circle to be 3 ohms away from the origin. Notice that the reach of the Mohs circle did not change and still extends as far as 18 ohms. Careful consideration needs to be taken when using the voltage memory polarization and expansion Mohs element for protecting transmission lines that are powered by a weak source with a very high source impedance. The power system shown here has a source impedance of 200 ohms, giving us a system impedance ratio of 10. If our Mohs characteristic is now expanded by an amount equal to the source impedance, our protection zone will cover a much larger area in the resistive direction. This extended zone may cause the D60 to incorrectly detect a fault when transients cause the impedance of the line to protrude into its zone of protection. Transients of this nature can occur in instances where the 3 poles of a breaker are opening or closing unevenly. If you are protecting a transmission line that is powered by a weak source so that your system will have a very high system impedance ratio, this expansion Mohs element should be disabled and a standard Mohs characteristic should be used. Another alternative is to use the quadrilateral characteristic where the shape and size of the zone of operation can be customized to fit your needs. The quadrilateral characteristic uses the voltage memory polarization to determine whether or not the fault is in its zone of protection. However, the voltage memory polarization does not alter the size or shape of the zone. This voltage memory polarization feature is used for all phase and ground distance protection elements for detecting the direction of faults that are located at the beginning of the transmission line and close to the measurement point. As mentioned before, the D60 uses the voltage to detect the direction of current flow for all Mohs and quadrilateral zones of protection and to determine the size of the zone of protection for the Mohs circle characteristic. If there is an actual voltage that can be read by the relay, the D60 will use this for the directional comparison. If there is no voltage present, the D60 will use the voltage that was recorded before the fault. This is also known as the memorized voltage. The recording or memorizing of the voltage is performed in the following way. In order for the D60 to begin recording, the positive sequence voltage must be between 80 and 115% of the nominal voltage level. The D60 also verifies that this voltage signal is not distorted in any way before it starts recording. Next, the non-distorted voltage must be available for 5 cycles before recording will begin. Finally, once the 5-cycle criterion is established, the memory is continuously updated with the latest voltage data. Once a 3-phase fault occurs, the positive sequence voltage will drop to below 80% of the rated voltage, and the voltage memory circuit will operate in the following manner. The D60 will detect the positive sequence voltage has dropped to below 80% of the rated voltage. The recording of the voltage will stop, and the memorized voltage will now be equal to the last voltage recorded before the fault. The memory duration timer, which determines how long the memorized voltage will be used, starts to time out. This duration time is set in cycles and is programmable by the user. The setting of this timer will be demonstrated in a later example. The memorized voltage will now be used in all directional comparisons. Once the memory duration timer expires, the memorized voltage feature works in the following way. The D60 checks the magnitude of the positive sequence voltage. If the positive sequence voltage is below 10% of the rated voltage, the last voltage recorded continues to be used for directional comparisons. If the positive sequence voltage is above 10% of the rated voltage, the actual voltage is now used for directional comparisons. When configuring the length of the memory duration setting, which sets the amount of time the memorized voltage will be used at the time of a fault, the following variables must be considered. The memory duration timer must be set to be long enough to ride through the maximum fault clearing time of the substation, including the breaker fail time. On the other hand, the memory duration cannot be set so long that power system events such as power swings and natural drift of the system cause the distance functions in the relay to incorrectly operate. When testing your D60 relay, the voltage memory feature may cause the relay to operate not as you expected. In order to ensure you are testing your D60 properly, the following recommendations should be followed. First, make sure that your VT secondary rating settings are entered correctly. Secondly, when testing the distance elements, apply pre-fault voltages of at least 80% of nominal to the relay and ensure the pre-fault current and voltages are present for at least 7 cycles. Finally, take into consideration that once the memory expires, the initial resistive fault coverage and directional integrity may be lost and may cause unexpected operations for longer-lasting faults.